perfectly inelastic collision in one dimension. Perfectly inelastic collision in one dimension. Okay. A collision is said to be perfectly inelastic. A collision is said to be a collision is said to be perfectly inelastic. Perfectly inelastic if the two particles stick together after collision. A collision is said to be perfectly inelastic if the two particles stick together after collision. Okay. We shall discuss the problem in the laboratory frame as well as in the center of the frame. Okay. First point. Laboratory frame. Okay. Let m1 and m2 be the masses and e1 into the velocities of two particles before collision. Since the two particles stick together and impact, let their velocity after collision be vector v. Initial linear momentum of mass m1 moving with a velocity e1, then e1 vector equal to m1 e1 vector, the linear momentum p, vector p, linear momentum vector p equal to m1 e1 vector, initial linear momentum of mass m2 at rest. Okay, initial linear momentum of mass m2 at rest equal to 0. Okay. Let the combined mass m1 plus m2. Let the combined mass m1 plus m2 move with a velocity vector v in the initial direction, then final linear momentum, then final linear momentum of the system is m1 plus m2 vector v. Okay. According to the principle of conservation of linear momentum, according to the principle of conservation, a principle to the conservation of linear momentum, m1 e1 vector equal to m1 plus m2 v vector is that vector v equal to m1 upon m1 plus m2 e1 vector. Okay. Kinetic energy of m1 before collision. Kinetic energy of m1 before collision. Okay. Before collision equal to 1 upon 2 m1 e1 square. Kinetic energy of m2 before collision is 0. Kinetic energy of m1 before collision 1 upon 2 m1 e1 square. Okay. And kinetic energy of m2 before collision collision equal to 0, okay? Because M2 is at rest, okay? Total kinetic energy before collision. Total kinetic energy before collision. Total kinetic energy before collision. T1 equal to 1 upon 2 m1 u1 square, okay? Kinetic energy of combined mass. Kinetic energy of combined mass m1 plus m2 after collision, okay? After collision, T2 equal to 1 upon 2 m1 plus m2 v square. 1 upon T2 equal to 1 upon 2 m1 plus m2 v square equal to 1 upon 2 m1 plus m2 m1 square u1 square upon m1 plus m2 whole square, okay? Is that 1 upon 2 m1 square upon m1 plus m2 u1 square. So T2 upon T1, okay? T2 upon T1. That means 1 upon 2 m1 plus m2 v square, m1 plus m2 v square upon T1 is 1 upon 2 m1 u1 square, 1 upon 2 m1 u1 square, okay? That is T2 upon T1 equal to m1 upon m1 plus m2, okay? As m1 is less than m1 plus m2, then T2 is less than T1. The final kinetic energy is that the final kinetic energy after collision is less than the kinetic energy before collision in the lab system, okay? In the lab system, okay? Decrease in energy, okay? 1 minute. Decrease in energy, okay? Decrease in energy, okay? Decrease in energy. The decrease in energy E equal to T1 minus T2 equal to 1 upon 2 m1 u1 square minus 1 upon 2 m1 square u1 square upon m1 plus m2. Is that 1 upon 2 m1 m2 upon m1 plus m2 u1 square. Is that 1 upon 2 mu u1 square. This is the equation number first, where mu equal to m1 m2 upon m1 plus m2, okay? m1 plus m2 is reduced mass, okay? Good. 1 minute. Second point, center of mass frame. Center of mass frame, okay? Velocity of center of mass velocity of center of mass equal to m1 u1 vector upon m1 plus m2, where u2 vector equal to 0. Velocity of m1 before collision. Velocity of m1 before collision. Okay, in centimeter, in center of mass system, equal to u1 dash vector equal to u1 vector minus b cm vector, u1 vector minus b center of mass vector. Okay, so u1 minus m1 upon m1 plus m2, and u1 vector equal to m2 upon m1 plus m2 u1 vector. Okay, velocity of m2 before collision. Velocity of m2 before collision. In center of mass system, u2 dash vector equal to u2 minus b vector, bcm vector equal to minus bcm vector equal to minus m1 upon m1 plus m2 u1 vector. Okay, because the velocity, second velocity is 0. Okay, after collision the two particles stick together and the combined mass m1 plus m2 move with a velocity equal to the velocity of center of mass with respect to the lab, okay, system, and is at rest with respect to the center of mass system itself. Hence, according to the principle of conservation of linear momentum, m1 u1 vector plus m2 u2 dash vector equal to 0. The final linear momentum, is 0. Okay, so m1 dash vector equal to minus m2 u2 dash vector. Okay, the initial kinetic energy, okay, initial kinetic energy of m1 in center of mass system, equal to 1 upon 2 m1 e1 dash square, and initial kinetic energy of m2 in center of mass system equal to 1 upon 2 m2 u2 dash vector, square. Okay, total kinetic energy, total initial kinetic energy in center of mass, total initial kinetic energy in center of mass system, T1 dash equal to 1 upon 2 m1 e1 dash square plus 1 upon 2 m2 u2 dash square. Okay, final kinetic energy of combined mass, kinetic energy of combined mass m1 plus m2 equal to T2 dash equal to 0. m1 plus m2 at rest. Okay, in center of mass, decrease in kinetic energy. Decrease in kinetic energy. Kinetic energy E equal to T1 dash minus T2 dash. E equal to T1 dash minus T2 dash. The decrease in kinetic energy, but T2 dash equal to 0. So E equal to 1 upon 2 m1 E1 dash square plus 1 upon 2 m2 E2 dash square. Okay, and this is also changed in 1 upon 2 m1 1 upon 2 m1 m2 E1 upon m1 plus m2 whole square. Okay, plus 1 upon 2 m2 m1 E1 upon whole upon m1 plus m2 whole square. Okay, this is equal to 1 upon 2 m1 m2 upon m1 plus m2 E1 square, and this is changing 1 upon 2 mu E1 square, 1 upon 2 mu E1 square. Okay, where mu equal to m1 m2 upon m1 plus m2 is the reduced mass. Okay, this is the equation number second. This is the equation number second. This is the equation number second. Okay, and in equation number first, and in a laboratory frame, in a laboratory frame, laboratory frame, decrease energy equal to 1 upon 2 mu E1 square, and in center of mass frame E equal to 1 upon 2 mu E1 square. Okay, 1 upon 2 mu E1 square. Okay, the comparing this is the relation first, and this is the relation second. Comparing relation first and the relation second, we find that decrease in kinetic energy after collision is the same in the life system as well as in the center of mass system, Okay, and then comparing relations first and second, comparing relation first and second, we find that the decrease in kinetic energy after collision is the same in the lab system as well as in the center of mass system, Okay, next, this decrease in kinetic energy may appear as excitation energy of the scattered particles. Okay, this decrease in kinetic energy may appear as excitation energy of the scattered particles. Okay, it may also be noted that decrease in energy of the combined mass in center of mass system is equal to the initial kinetic energy of the particles in the same system. Okay, thank you. Next heading is velocity of particles in elastic collision.